Hello, everyone. We are Team 1 in Embedded Security and Hardware Hacking, completely insecure Alice, which stands for CIA. And I'm Ryan.
I'm Charlotte.
I'm Kelly.
I'm Sasan.
And because we don't have video capturing here are our faces.
Yay. So next coming up is an overview of our design.
So we have is, what we need to do is we need to secure a firmware payload so that some adversary can take a publicly released, publicly accessible update tool and install our encrypted firmware onto the bootloader without compromising the integrity of the bootloader or the integrity of the firmware. And so we do this by encryption, first of all, with both the initial and all additional updates, and we store the keys onto the bootloader when we are provisioning it in the factory, so that when it's released, it has the set of keys. We use both AES and RSA, so that if someone were to dump the keys out of our bootloader somehow, they would not be able to send their own updates as they are missing the RSA private key. For the actual firmware update process, what we do is we've packaged our firmware into 1,320 byte chunks, and of that, we'll go over the chunk specification more in depth later. But basically, each chunk has 8 bytes of metadata, which is first sent to the bootloader, which verifies that, oh, the version is correct, it's not a previous version, it's properly signed and whatnot. And if that's all good, then the firmware update will begin to send frames over to the bootloader, 16 bytes in each frame. And the bootloader just reading all that information until it receives all of the frames. Once that happens, it's able to then compute SHA-256 among it, verify the integrity of everything it's received, and if everything is good, it will put that chunk into a temporary firmware address. And once every chunk is received and everything is valid, then the temporary address firmware will be copied over to the main address, and the firmware update would have finished installing. As part of...
So we also wrote this really nice 10-page Google Docs documentation because we want people to be able to see our design and not be able to break it.
All right, so this on the defense side, as we said we would go over, this is the structure of each packet that we're sending. We use both AES and RSA because RSA has the benefit of the public-private asymmetric nature, so that, as said previously, leaking the public key won't really compromise our integrity. However, RSA itself cannot be used realistically to encrypt data as it has a very small maximum length. So we use AES for the actual encryption and then RSA for signing.
So here are the highlights of our design. We encrypted and signed each packet independently, and each packet has an index which ensures that it is in the right order. And as for RSA, we signed both the metadata and the firmware binary together, which provides more layers of security. And on the bootloader side, we made sure to verify the firmware size. So it first writes the firmware to a temporary address, and then once it is received, it verifies the number of bytes it received with the firmware size before writing it to the actual address.
So some still problems with our design is that we did not check for buffer overflow problems in our code, since that wasn't an attack that was covered before we wrote our design. And also, connecting to that, block ciphers are very prone to memory issues, and we assumed that signing would make the length trusted, and we didn't actually do any bounce checking with our inputs. So all of this, a fix for it would be to rewrite the code in variable assignment to test for buffer overflow, and also length check all of our inputs. In addition, our system also doesn't really handle bad inputs very well. It just resets if you send it something bad. So another thing we should do is that we should establish some better communication protocols for errors, like resending a packet of data if there was an error.
So something really interesting that happened was that none of the other teams actually attacked us, and there were even messages in the Zoom and in the Discord of people saying that they just kind of didn't really want to have anything to do with us. And interestingly enough, our structure is very similar to everyone else's, as we were all provided the same base insecure example. The only thing that we did really differently was we added lots of bells and whistles. Like we added a progress bar to the update tool, we added cutters, etc. But none of that actually helps security-wise. So, yeah, deterrence is not a substitute for security, but having deterrence can complement it.
Now we're going to talk about the attack phase, where we attack other teams' designs.
So one way we tried to attack was by sending an invalid firmware to the bootloader. And to do that, we first checked the source code and tried to understand the protocol to uncover security vulnerabilities. And while we're investigating other teams' design, we found that most teams were HMACing each of their firmware chunks separately, and therefore there is no security to the order at which the chunks are sent. So this can potentially be exploited if we manage to swap 2 or more of those chunks, and if we can do that correctly, we can successfully corrupt the firmware and send that to the bootloader.
So more specifically, this is the first attack that we did on the B team. The main issue with their implementation was that the metadata was encrypted and secured separately from the rest of the firmware, and therefore we could interchange the metadata of different versions. So we originally was going to target rollback and put the metadata of an earlier version onto put the metadata of a later version onto an earlier version to fool the bootloader to thinking that we didn't roll back. However, due to the problem with the length of the versions not fitting, this didn't actually work out. However, we realized in that putting in what is the wrong length, we actually managed to corrupt the firmware, and that's how we attacked the B team.
Right. For the B team, their actual firmware was actually secured really well, as they not only HMAC'd each chunk, but then they also HMAC'd all the chunks together and had 3 layers of HMACs on top of it. So that wasn't really interchangeable or modifiable like described in the previous slide. It's just that the metadata just so happened to be separate from that.
Mm-hmm. Yep. And then the second attack we did was on the goats. The idea of it is similar to the idea of attacking the B team. However, instead of targeting the metadata, we targeted the actual firmware. We realized that each firm the data was protected separately with HMAC, meaning that the order of the data is not actually protected. So for the attack, we took out the firmware size 0 version, went to the middle of it, we identified a 51-byte chunk. This was actually really easy because every single chunk ended with a null terminator. And then we swapped 2 chunks around with each other. And then we updated with this corrupted firmware. Since the order of the chunks are different, the entire firmware now decrypts differently, and now it's corrupted and invalid.
I'll just go restart this slide. So for the third attack, we targeted a team, error 404 brain not found, and their implementation was quite interesting in that what they would do is they would actually write the firmware data we send to them directly to the flash, and then after writing it, they would validate the HMAC, and if it was invalid, they would delete that page. So the issue with that was that flash erase will always erase 1 kilobyte, but when you send firmware, you don't have to send up the entire kilobyte. So what we did was we sent a little bit of correct valid firmware data, and then we stopped sending it and had to like validate the small amount of data we sent to it. It realized that it was not good, it was gibberish, and then it erased the entire page of flash, and therefore corrupting the existing firmware on the chip. The other thing for it was that, again, its metadata was separate from the actual firmware, so that's why we were able to modify the firmware while still passing the HMAC test for the metadata. We just used a good metadata and metadata HMAC, and then we sent bad firmware. And